All right, so we were talking about induction, so let's keep going with that. So remember the basic setup. Everybody turn in their homework?
Yes, sir.
By the way. Uh-oh. Someone did their homework upside down. Ooh, that's bad. All right, thank you. No. Yeah, right. All right. So remember the basic setup with mathematical induction. Given, and I'll start with a base case of 1 today just to hit the idea. The base case isn't really critical. Given P of 1 as a true proposition and P of n implies P of n plus 1, for all n bigger than or equal to our base case 1, we can conclude P of n for all n bigger than or equal to 1. And the thing that potentially confuses the issue sometimes is that this second statement is not the same as the third statement. The third statement is way more powerful, right? This says if P is true for n, it's true for n plus 1. This says P is true for all n. Okay? P of n could be the proposition that I am incredibly rich on my nth birthday, right? And we can probably prove that if I'm rich on my 30th birthday, then I will be rich on my 31st birthday, because I'll hire someone to not let me spend all my money, right? But that does not prove that I am rich for every birthday from my first birthday on, right? Even though this is true, if I'm rich on birthday n, I'll be rich on birthday n plus 1. That is true, but I can't conclude this unless I also know that I'm rich on some birthday, right? And if I don't have this base case, the inductive step doesn't get me the conclusion that P of n is true for all n. So we always need two things to do induction. We need the base case, and we need the inductive step. And if those are true, then we can conclude the proposition is true for all n. But it's usually easier to prove the inductive step than to prove the conclusion we're after. Okay, so let's do some more examples, and let's go back to some mathematics. Let P of n be the proposition 1 plus 2 plus 3 plus ... plus n, the sum of the first n integers, is equal to n times n plus 1 divided by 2. So P of n is a proposition about adding up integers. And it says if you add the first n integers, you get n times n plus 1 over 2. So sum of the first 100 integers, this claims, is equal to 100 times 101 divided by 2. And that may or may not be true. But we'd like to prove that this is true for all n bigger than or equal to 1. So prove P of n for all n bigger than or equal to 1. Now P of n is not the proposition that this is true for all n bigger than or equal to 1. P of n is a proposition about a particular value n. P of 5 is the proposition that 1 plus 2 plus 3 plus 4 plus 5 is equal to 5 times 6 divided by 2, 15. What we want to prove is that P of n is always true for any n bigger than or equal to 1. And we can do this with mathematical induction. Okay, how do we prove a proposition is true for all n bigger than or equal to 1? Prove it's true for 1, and prove if it's true for some n bigger than or equal to 1, it's true for n plus 1. Prove that we can make this step from n to n plus 1.
prove proposition of n plus 1.
Effectively, yeah, it could be proposition of 0, it could be proposition of n implies proposition of n plus 2 if we wanted to make a
Right.
statement about even integers, for example.
Got it.
But yeah, there's some base case and then there's some way to move from one step to another step, an inductive step. Most everything we do will be p of 1 and p of n goes to p of n plus 1. Okay, let's look at the base case. P of 1 is the proposition. Well, how do we find p of 1? Just substitute a 1 in for n and write down the proposition. Well, this says the sum of the first 1 integers, so like 1 added up to 1, is equal to 1 times 1 plus 1 over 2. So formally speaking, that's what p of 1 says. The proposition that 1 is equal to 1 times 1 plus 1 divided by 2. Is this proposition true or false? Is 1 equal to 1 times 1 plus 1 over 2? That's true, right? 1 times 2 divided by 2, that's just 1. 1 is equal to 1. This is true just by pulling out our calculator or something. So p of 1 is true. We have a base case. So prove the following. Prove that if n is any number bigger than or equal to 1, and if we assume p of n is true, then p of n plus 1 is also true. Okay, so this is the real heart of our proof. So let's prove this. Well, my first statement of my proof is going to be p of n is true. Why? That's a hypothesis. Well, I can't really do anything with p of n unless I know what it says, and then maybe I can do something with what it says. So step 2, almost always I'm going to write out what p of n says. Since I know p of n is true by hypothesis, then I know the following: 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 divided by 2. The reason for that, that's the definition of p of n. Now I'm going to do something without going through why I'm doing this, but I'm going to do something that hopefully you'll agree is still valid, and then we'll come back and talk about why we did this. I know that this left side is equal to the right side. I'm going to add something to both the left and right side. I'm going to add the same thing to both sides, so that equality should still hold. This is just plain old arithmetic at this point. Nothing up my sleeves, so whatever I add to the left, if I also add that to the right, everything is still equal. So I'm going to do the following: 1 plus 2 plus 3 plus ... plus n plus 1, and that's going to be equal to what the right hand side was, n times n plus 1 over 2, also plus n plus 1. And the reason for this, adding same thing to both sides. Or you could say properties of arithmetic, or properties of addition, or properties of equalities, or it's obvious, but don't ever say it's obvious in a proof. But I'm just adding the same thing to both sides. So this is definitely a true proposition. Everybody agree with that? Okay. I'm throwing some parentheses around the n plus 1. That's not going to change anything. I'm going to rewrite the right-hand side using algebra. So I'm going to change this to be n squared plus n over 2 plus n plus 1. and I'm going to find a common denominator and write this as n squared plus n over 2 plus 2 times n plus 1 over 2. And I'm just going to come right down here on the next line and say that's also equal to n squared plus 2n, n squared plus n plus 2 times n plus 1, all divided by 2, which is n squared plus n plus 2n plus 2, all divided by 2. So I'm just doing algebra here. We're just simplifying this expression, which is equal to n squared plus n plus 2n is 3n plus 2, all divided by 2. And now I'm going to factor and say this is n plus 1 times n plus 2, all divided by 2. And the reason for that is algebra. So I have a new proposition. This is the sum of the first n plus 1 integers, and I've proven that's equal to n plus 1 times n plus 2 divided by 2. This is assuming that p of n was true. Right? This could all be garbage. But assuming p of n is true, I've proven the sum of the first n plus 1 integers is n plus 1 times n plus 2 divided by 2. Okay, let's go back and look at our original proposition, p of n. P of n is the proposition that the sum of the first n integers is n times n plus 1 over 2. Without worrying whether it's true or not, what does p of n plus 1 say? Yeah, so if this is p of n plus 1 says 1 plus 2 plus 3 plus all the way up to n plus 1 equals, if I just plug it straight in, it's n plus 1 times n plus 1 divided by 2. That's n plus 1 times n plus 2 over 2. That's what p of n plus 1 says. Oh, I smeared it. P of n plus 1 says the sum of the first n plus 1 integers equals n plus 1 times n plus 2 over 2. Well, what have I just proven? The sum of the first n plus 1 integers equals n plus 1 times n plus 2 over 2. I've just proven p of n plus 1. So I can write this down as a fifth step of my proof, p of n plus 1, and that's because of the definition of p of n plus 1. All right, so what's happened? I started off by assuming p of n. I've just proven p of n plus 1. So therefore, p of n implies p of n plus 1. And this holds for any n bigger than or equal to 1. That was my only assumption. Doesn't make sense if n is negative or 0. Well, now I've got two things. I've proven a base case, p of 1 is true, and I've proven if p of n is true, then p of n plus 1 is true. Now, I can say by mathematical induction, because I proved p of 1 and I proved p of n implies p of n plus 1, I can conclude p of n for all n bigger than or equal to 1. The reason for that is mathematical induction. And that's what we were trying to show. The reason we know this if-then statement is just we proved starting with step 1, we proved step 5. So that's a classic proof using mathematical induction. Do the mechanics of that make sense so far? Not necessarily the intuition, but just the mechanics. Some of these proofs can leave you feeling completely uninspired as to why this is true. But if you follow step by step, you're kind of forced to nod your head and acknowledge, yes, step 2 is true, proposition 3 is true, proposition 4, that's true, I guess this is true also. Right? And we may not understand why that is, but if each step follows logically from the steps before, we have no choice but to accept the final conclusion. So here's the thing. When we were doing this proof, this was really the bridge. Step 1 and 2, that was just writing down P of n is true and then expanding what P of n says. And once we got through step 3, then we started doing algebra, and very quickly what came out the other end was P of n plus 1. The real sort of question is, how did we decide to add n plus 1 to both sides? That was exactly the right thing to do to let this thing turn into P of n plus 1. So most inductive proofs, there's stuff you do in the beginning that's pretty mechanical, and then there's some moment of inspiration, and then on the other side of that moment there's more mechanical stuff. Okay, so there's kind of like pre-inspiration, post-inspiration. The trick is making that bridge from that first part to that second part. And it's usually something like add n plus 1 to both sides, or put in a blender and frappe for 3 minutes, something. And then all of a sudden, it's a series of mechanical steps to go through to get to P of n plus 1. Now, if I ever write down P of n plus 1 as one of my statements and I haven't proven it, my proof is invalid. Okay, if you're trying to prove P of n plus 1, you can't write down P of n plus 1. You can write down things that you know are true, and if from there you can show P of n plus 1 is true, that's your goal. But you can't just arbitrarily write down the thing you're trying to prove. In a proof, you can only write things that you're assuming or things that follow from what you've already written. Okay, that's probably the most important thing about proofs. You can only write down things that you're assuming are true or things that follow from what you've already written, what you've already shown to be true. So if I write P of n plus 1, my proof is invalid at that point. But I did not write down P of n plus 1 arbitrarily. What I did was I took a statement I knew was true, I added the same thing to both sides. This is true because of what I already showed was true. And then from here, I showed P of n plus 1 was true. Okay, but how did I know that I should add n plus 1 to both sides? Well, I peeked. Okay? In my head, I went ahead and I said, well, what does P of n plus 1 say? Well, this side should be added up to n plus 1, and this side should look something like this. Okay, so you can peek on your exams, on your proofs. Well, on your exams on proofs also. Yeah. So here's what you can do. You can write a section of your proof and label it ignore. And you can put anything in there that you want. And I'll still look at it, but I won't consider it to be part of your proof. So you can write things that you haven't proven, you can write things that are incorrect, you can write things that are completely false, right? This is not going to be considered part of your proof. This is, right? But if you want some scratch area to think things out, right, mark off a little area and label it ignore. And here's what I would have done in this question. In my ignore area, I would have decided, what does P of n plus 1 say? P of n plus 1 says, 1 plus 2 plus 3 plus n plus 1 equals n plus 1 times n plus 2 over 2. It's okay to write it here because it's not part of my proof. If I write it over here, my proof is not valid because I don't have any reason to know that this is true yet. I've written a proposition that's unproven. Everything that follows is unproven. But I can write it over here. Okay, well, I had this. I know that statement 2 is true. And I know that I want to get to where I can say that this is true. And I don't know how to turn n times n plus 1 over 2 into n plus 1 times n plus 2 over 2, but I have a pretty good idea how to turn 1 plus 2 plus n into 1 plus 2 plus n plus 1. All I got to do is just add this little extra bit onto the end of this. And so that's what I did over here, but to keep this in equality, I had to also add it onto the right side. That may or may not have been a good thing to do. It's not an incorrect thing to do, though. Right? It's still a valid statement that I've written. Now I work with the right side, and I hope that I can turn it into something like this. Well, I got a 2 on the bottom. I got a 2 on the bottom here. So that says let's put this over a common denominator. Let's combine, and let's see if we can turn it into this form. And you can. Right? And you might do a lot of that work over in the scratch area and then say, oh, okay, I get it. And now you fill out what the next steps are. And you work your way to a nice clean proof.
Can you disprove things using mathematical induction as well? So say you did that and it wasn't true.
If you did this, well, if you could prove that this was equal to, you know, n times n plus 1 times n plus 5 over 7 or something, right, then you could use that to say it's not equal to this formula. But I think you can probably use the idea to actually directly disprove things too. But you're just proving the negation of a proposition.
Doesn't seem as useful for us. We're just trying to
It might
some
be.
recursion,
Yeah,
use a
yeah,
sequence or something like that.
yeah. That's an interesting idea. All right, so let's look at some examples where this kicks in. So 1 plus 3 plus 5 plus ... plus 2 times n minus 1, where n is bigger than or equal to 1. Well, this sequence I've written here on the left is the sum of the first n odd integers. For example, if n is 3, this says 1 plus 3 plus 5. If n is 5, it'll be 1 plus 3 plus 5 plus 7 plus 9. So this thing on the left is the sum of the first n odd integers. And I'm claiming that's equal to n squared. So 1 plus 3 plus 5, 4 plus 5 is 9, that's 3 squared. 1 plus 3 plus 5 plus 7 is 9 plus 7 is 16, that's 4 squared. So this seems like a reasonable formula. It works for 2 cases at least. So how do we prove that this is true for all n? Well, make a proposition. You always have to start with a proposition. You can't write anything about P of 1 or P of n until you've told the person what P of n is. So probably the first step of any proof like this is to state the proposition P of n, or Q of n, or whatever you want to call it. Right? So I'll call this P of n. Let P of n be the proposition that the sum of the first n odd integers is equal to n squared, where n is bigger than or equal to 1. Okay, so let's find a base case. P of 1 says 1, that's the sum of the first odd integer, is equal to 1 squared. And that is true, because 1 is equal to 1. So now we need to prove that P of n implies P of n plus 1 for all n bigger than or equal to 1. And it's going to look a lot like what we just did with the sum of integers. So step 1, I'll state P of n. That's a hypothesis. Step 2, I'll spell out what this says. 1 plus 3 plus 5 up to 2n minus 1 is equal to n squared. That's the definition of P of n. And I'm going to put my ignore area here. I want to prove P of n plus 1. Well, the left side should be 1 plus 3 plus 5 plus 2n minus 1 plus one more odd integer, which is going to be what? What's the integer after 2n minus 1? 2n plus 1. And that should be equal to n plus 1 squared. So here again, my left-hand side that I'm after looks a lot like a left-hand side I already have in my proof. If I just add another 2n plus 1, maybe I can turn it into what I'm after. So let's do that. So I can write this statement, and I know it's true because all I did was add 2n plus 1 to both sides. And I'm just going to expand that right-hand side. I'll get rid of my parentheses. It's n squared plus 2n plus 1, and how can I rewrite that in a way that might be useful? Equals n plus 1 squared. That's more algebra. But hey, what have we just proven? Just by assuming P of n, we've proven that the sum of the first n plus 1 odd integers is equal to n plus 1 squared. That's what P of n plus 1 says. So we've proven P of n plus 1. And so now we can say, given P of n plus 1 is also true. And now we can say P of n itself is true for all n bigger than or equal to 1. That's mathematical induction. And we're done. And a lot of times we use induction without even realizing it. Now this, right, we learn these formulas sometimes in other classes. If you add up consecutive integers, you get a triangle number. It's n times n plus 1 over 2. If you add odd integers, you get a square. But sometimes there's things that are very obvious to us. But the reason they're obvious to us is because we're actually using mathematical induction and probably not even realizing it. So let me give you an example of something that we pretty much know is true. But we may never have proven. So what's plus 1? 1 plus 1 equal to? 1 plus 1 plus 1? 3. If I add n ones together, what am I going to get? Somebody else. I'm going to get n. If I add 7 ones together, I'm going to get 7. Does everybody believe this? If I add 1,519,286 ones together on my calculator, I'm going to get 1,586,218. Does everybody believe that? Has anybody ever done that? How do we know it's true?
True for the base case and true for the base case plus one.
Yeah. Let P of n be the proposition 1 plus 1 n times equals n. And we'll do this where n is some number bigger than or equal to 1, or maybe 2. Well, P of 1 is true, right? If we just add 1, 1, we just get 1. Well, suppose you know that if you add 1, 1, you just get 1, and now you want to know if you add 2 1s, will you get 2? Well, you can add up 1, 1, and you get 1. Add 1 to that right side, that left side, so now you're adding 2 1s, and that's the same as adding 1 to your right side. You should get 1 plus 1 is 2. Well, if I know 1 plus 1 plus 1 is equal to 3, and I want to know what 1 plus 1 plus 1 plus 1 is equal to, and I don't want to use my calculator, well, I know that if I add these first 3 ones, I'm going to get 3, and so this should just be 3 plus 1. And once I know what the sum of 4 ones is, if I want to know what the sum of 5 ones is, I take the sum of 4 ones, which I just showed was 4, and I just add 1 to it. So if you wanted to prove that the sum of 100 ones was equal to 100, you could do it in 100 steps, right? So let P of n be the proposition that n ones adds up to n. We know P of 1 is true. Assume P of n. So if we add n ones, we're going to get n. That's what P of n says. Well, if we add n plus 1 ones, so we take our n ones and we add 1 more, we're going to get n plus 1. And that's what P of n plus 1 says. So we know how to go from n to n plus 1, and we understand that if we can get to n plus 1, we can get to n plus 2, we can get to n plus 3, we can get to n plus anything. But if we want to get to n plus 1,000,000, it takes us 1,000,000 steps. Mathematical induction says you don't have to do 1,000,000 steps. Right? If you can get from n to n plus 1, you can get to anything bigger than or equal to n. So it takes that intuition and sort of bundles it in a rigid form for us.
So for your base case, you prove for something like, say, like n is 3, but you couldn't prove for 2 or 1, because it implies that n plus 1 is the new lower bound for which n is true.
Yeah, so if you can prove it for n equals 3, and then prove n implies n plus 1, then you can conclude P of n for all n bigger than or equal to 3.
Okay.
But it may not be true for 2 or 1. All right, let's go back to 250. We have De Morgan's theorem. If you take A, B, you AND them, and you take the complement, you get the OR of the complements of A and B. Okay. Have you seen the 3-variable version? If you take the complement of the AND of 3 variables, that's the same as ORing the complement of all 3 variables. Have you seen the 4-element version? And there's a 5-element and a 6-element, and this works for 100 elements or 1,000 elements, right? And we can prove that. So let's prove it for 3 elements. Let's suppose we know De Morgan's theorem for 2 variables. Okay, so given this, let's find what this is equal to. Well, A ANDed with B ANDed with C, all the complement of it, is also this one thing AB ANDed with this thing C, all complemented. De Morgan's theorem, right, A is just, it's got a binary value, but AB is a thing with a binary value, right? So if I treat this as the first term and I treat C as the second term, De Morgan's theorem on 2 variables tells me this is equal to the complement of the first thing ORed with the complement of the second thing. That's just 2 variable De Morgans. But I can apply that again, and 2 variable De Morgans tells me AB bar is equal to A bar or B bar. And I've still got my or C bar. I just proved the 3 variable version. Can we prove a 4 variable version? ABCD bar is equal to this thing ANDed with that thing complemented. 2 variable De Morgan tells me this thing ANDed with that thing complemented is the complement of the first thing, ORed with the complement of the second thing. And given 3 variable De Morgan, ABC bar is just A bar or B bar or C bar, and we OR with D bar, bang, there's the proof of the 4 element De Morgan. Now suppose your final exam in 250 is one question which says prove the 10 variable version of De Morgan's theorem. Could you do that? If you know this, if this is on your page of notes, you just keep going. You do 6 more steps. Take this, throw an E in there, it's ABCD ANDed with E, that's the complement of ABCD, ORed with the complement of E, and the complement of ABCD is this thing. Now you got the 5 element version. Each line of your proof gets a little longer, but it's still just 6 more lines you have to write till you'll have the complement of A through J is equal to the OR of their complements. And if for bonus points you could prove the 100 variable version of De Morgan's, you could do that. It would take 100 lines of total proof. And once you've done that, you can probably convince yourself that you could do this for any number of variables, say bigger than or equal to 2. But to actually do that and get credit on a test, right, you'd have to fill out that many lines of proof. Mathematical induction lets you bundle that into a single proof.
So we can't just use the 2 element to prove the 4.
You could break this down using the 2 element version, right, to be this and that, and then you could work backwards from there.
I just didn't want to write it, I didn't want to do the second to prove the 3rd.
Oh, okay. Yeah, you could do it. You could do it directly from the 10th. You could do it as a 5 and a 5 and break those down. That would be cool. So mathematical induction basically gives us a formal way to phrase the following. You can do this in general for any number of variables. Just keep doing this. Okay? Just keep doing this doesn't work for a formal proof. Right? Unless the way that you phrase that is by mathematical induction. But by mathematical induction basically means just keep doing this. And when there's something you're trying to prove and you can see I could keep doing this process again and again and eventually get to the final answer that I'm trying to prove, chances are you can throw mathematical induction at it. So let's just formalize this particular example. Let P of n be the proposition and I'll call my terms x0. I'll call them x1, x2, up through xn. Bar is equal to x1 bar or x2 bar up to xn bar instead of a, b, c, d, e. And we want to prove p of n for all n bigger than or equal to 2. It's kind of silly true for one variable, because that just says x1 bar is equal to x1 bar. But we'll start with two variables, just to make it a little more profound looking. So base case, p of 2 says x1, x2 bar equals x1 bar, or x2 bar. Is that true? Yes, that's De Morgan's theorem. We got our base case. Okay, so now we want to prove p of n implies p of n plus 1 for any n bigger than or equal to 2. Well, step 1, p of n, that's our hypothesis. Step 2, x1, x2, dot, 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 xn bar equals x1 bar or x2 bar or up through xn bar. That's the definition of p of n. This is what we're trying to prove, right? But we're not going after a proof of this directly. We're using mathematical induction. So right now, all we're proving is that if p of n is true, p of n plus 1 is true. We're proving you can go from n variables to n plus 1 variables. And we did that a few times already a few minutes ago. We're just going to write that down as part of our proof. So x1, x2, dot, 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 xn, ANDed with xn plus 1, all complemented, is equal to these two things ANDed together, all complemented, which is equal by the two-variable version of De Morgan's theorem to x1, x2, dot, 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 xn, all complemented, ORed with xn plus 1 complemented. That's the two-variable De Morgan's theorem, DMT. And this left-hand side, since we know p of n is true, we're assuming that this left-hand side is equal to the sum of the complements plus xn plus 1 bar. So this gave us this, and this just gave us that. And so we've proven the complement of the and of the first of the n plus 1 variables is the or of the complements of those n plus 1 variables. That's p of n plus 1. That's the definition. Statement 3 was just Boolean algebra and De Morgan's theorem. And so we've proven p of n plus 1. So p of n implies p of n plus 1 for all n bigger than or equal to 2. Therefore, p of n for all n bigger than or equal to 2. That's mathematical induction. That's what we were trying to show. So if you can work something in particular cases, induction might let you generalize it to all cases. That's sort of the punchline. Suppose we add up powers of 2. So 1 plus 2 plus 4 plus dot 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 plus, let's go up to 2 to the n minus 1. So this is the sum of the first n powers of 2. And so what's the formula for what this is equal to? It's Calc 3, it's maybe CSE 121, it's probably Engineering 250. This is equal to 2 to the n minus 1, 1 less than 2 to the n. For example, if n is equal to 4, this left side is equal to 1 plus 2 plus 4 plus 8, right, up to 2 to the third. 1 plus 2 plus 4 plus 8 is 15. That's 1 less than 2 to the fourth, 16 minus 1. This is why n ones in binary corresponds to 2 to the n minus 1. 8 ones is 255, 16 ones is 32767, and so on. Or 65, 535, and so on. So we can prove that using mathematical induction. Let's prove it for n bigger than or equal to 1. Well, P of 1 says if n is equal to 1, this should be 1 plus 2 plus 4 up to 2 to the 0. 2 to the 0 is what? 1. So this just says 1 is equal to 2 to the n is equal to 1, 2 to the 1 minus 1. And 1 is equal to 2 minus 1, so this is true. So now prove P of n gives us P of n plus 1. Well, step 1, P of n, that's a hypothesis. Step 2, bless you. Step 2, we'll just write out the definition of P of n. And I'll go to my ignore scratch area over here. So what does P of n plus 1 say? Well, if n plus 1 is popped in here, n plus 1 minus 1, this is going to be the sum up to 2 to the n. And that should be equal to 2 to the n plus 1 minus 1. That's what I want to show. Well, how do I go from this to that? I'm just going to add 2 to the n. So add to the n to both sides. And I've got the sum of the first n powers of 2. And it's 2 to the n minus 1 plus 2 to the n, which is 2 to the n plus 2 to the n minus 1. 2 to the n plus 2 to the n is just 2 times 2 to the n. And 2 times 2 to the n is 2 to the n plus 1. And now I've shown that this is equal to that. Well, what is that? So this is algebra. This is P of n plus 1. So P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. And we're done. Okay, it doesn't always look exactly like this, but half the induction proofs you'll encounter are exactly like this. But we can do different things. So let's look at how 2 to the n and n factorial compare to each other. Suppose n is equal to 0. What's 2 to the 0 again? Okay, what is 0 factorial? Yeah, that's kind of annoying, but there's a good reason for it. So if n is equal to 0, 2 to the n and n factorial are equal. What about 1? 2 to the 1 is 2. What's 1 factorial? 1. 2 to the n is bigger. What about n equals 2? 2 squared is 4. What's 2 factorial? 2. 2 to the n is still bigger. What about 3? 8 and 6. Looks like 2 to the n is always bigger than n factorial, right? What about 4? 16. 4 factorial? 6 times 4, 24. So n factorial is just first n numbers multiplied together. So 2 to the n is less than n factorial for n equals 4. For 5, this is 32. This is 120. For 6, this is 64. This is 720. And not only from this point on down does 2 to the n look smaller than n factorial, it's really losing the race. It's getting significantly more smaller. Don't tell my English teacher. As n gets bigger. This is important, for example, when you're developing algorithms. You may have an algorithm whose time complexity is fundamentally 2 raised to the size of the thing you're processing. And you may have another algorithm whose time complexity is changing according to the factorial of the number of things you're processing. And for small values of n, 2 to the n might be slower. But eventually, 2 to the n is going to be a lot smaller than n factorial. And if we get out to 100, right, 2 to the n is going to be a whole lot smaller than 100 factorial. So we can state a proposition. Let P of n be the proposition which says 2 to the n is less than n factorial. And we can claim that P of n is true for all n bigger than or equal to 4. And we'd like to prove that. And it certainly seems to be true. Well, why is this happening? Why is this column growing so slowly and this is growing so quickly? Why do I have confidence that when I write down my values for row 7, that this is still going to be smaller than that?
You mean like intuitively?
Yeah.
Because you're multiplying the 2 to the n by 2 every time. As the factorial grows, you're multiplying by 8 or 9.
Yeah.
Or 10,
In this column, I'm going to multiply my previous number by 2. I'm going to multiply that previous number by 7, which is a whole lot bigger than 2. Since this factorial was bigger than 2 to the n to begin with, if I multiplied them both by 2, my n factorial would still be bigger. But if I multiply this column by 2 and I multiply my factorial by something even bigger than 2, it's going to be a whole lot bigger, right? That's the intuition. And if I wrote this out 100 rows, I could apply that intuition in every row. I'm just going to keep multiplying the left by 2 and the right by something bigger than 2. This inequality is going to get more and more significant. But I don't want to do that 100 times or 1,000 times. So we can prove this using induction. So we make a proposition. P of n is the proposition that 2 to the n is less than n factorial. And we want to prove P of n for all n from this point on down. So we prove that if we assume P of n, then this proposition is also true for n plus 1. We'll kind of start off the same way. Step 1, P of n, that's the hypothesis. Step 2, state what P of n says. 2 to the n is less than n factorial. That's the definition of P of n. And I may need an ignore section over here. Well, P of n plus 1 says 2 to the n plus 1 is less than n plus 1 factorial. Yeah?
Sorry, I'm just checking. We're using P of 4 as our base case?
P of 4 is the base case, yeah, because that's the first time that 2 to the n is less than n factorial.
And you're not showing the proofs up there.
Oh, yeah. Prove So, base case. There we go. Thanks. All right, so P of 4 is true. Well, so the intuition we just talked about was when I go from 2 to the n to 2 to the n plus 1, I'm multiplying by 2. When I go from n factorial to n plus 1 factorial, I'm multiplying by n plus 1. And since n is bigger than 4, it's definitely bigger than 2, and n plus 1 is definitely bigger than 2. So we want to formalize that somehow without waving our hands too much. So let me do this. 2 to the n plus 1 equals 2 times 2 to the n. That's the definition of 2 to the n plus 1. And since 2 to the n is less than n factorial, and I multiply by 2, 2 times 2 to the n is going to be less than 2 times n factorial. That's just properties of inequalities. And 2 times n factorial is certainly going to be less than n plus 1 times n factorial, because I know n is bigger than or equal to 4, so n plus 1 is bigger than 2. So another property of inequality, and this right-hand side is n plus 1 factorial. So that's algebra and properties of inequality. But what I've just shown by assuming P of n is that 2 to the n plus 1 is less than n plus 1 factorial. And that's P of n plus 1. And so by assuming P of n, we can prove P of n plus 1, and therefore P of n for all n bigger than or equal to 4. That's mathematical induction. And that's what we wanted to show. Yeah.
Where did the n go on the left side of the equal sign?
Over here?
No, other
Over here?
Yeah, I'm a little confused on that stuff.
Okay, so 2 to the n plus 1 is 2 times 2 to the n. Okay, and since 2 to the n is less than n factorial, 2 times 2 to the n is less than 2 times n factorial. Right? And since n is less than n plus 1, 2 times n factorial is less than n plus 1 times n factorial. And this, n plus 1 times n factorial, is n plus 1 factorial. Right? Product of the first n integers times n plus 1. Okay?
See it.
Cool. And that third step we could do a variety of ways. The inequality is so gross that there's different ways we could get there. But it's basically taking our intuition, right? If we multiply by 2, that's much smaller than if we multiply by n plus 1. Originally the right side was bigger, and now it's going to be even more bigger. Bigger. But that's a formal proof.
Will we ever do an example with this, like say finding the depth of a binary search tree or something like that? Like how would you apply it?
Oh yeah.
Okay.
Yeah. Yeah, we may not do that in here right now, but assuming we get to trees later on, which we might, we'll do it there. Or we might do it in 222. But it would apply perfectly. Okay, given an infinite number of 3-cent and 5-cent stamps, prove you can make any postage of 8 cents or greater. So you're mailing a package and you've got nothing but 3-cent and 5-cent stamps, and you're going to take it to the clerk and they're going to weigh it and they're going to say it costs $2.71. There's some combination of 3-cent and 5-cent stamps that will give you exactly $2.71. Or 8 cents or 9 cents or 10 cents or any number of cents, 8 or greater. And we can prove this using mathematical induction.
Exactly.
Exactly, yeah, with nothing left over. And we can try some examples, right? 8 is equal to 3 plus 5, 9 is equal to 3 plus 3 plus 3, 10 is equal to 5 plus 5, 11 is 5 plus 3 plus 3, 12 is 3 plus 3 4 times. How do we know it works for any number? So we can do an inductive proof. Let P of n be the proposition. You can make any postage of 8 cents or greater. You can make any postage of n using 3 cents and 5 cents. Don't do this on your exams or homeworks. I'm being sloppy. Let P of n be the proposition. You can make postage of n cents using 3-cent and 5-cent stamps. Okay, we need a base case, okay, and this is for prove P of n for all n bigger than or equal to 8. So we need a base case. P of 8 is true. Why? Because we just did it up there. You take a 3-cent and a 5-cent. Okay, so let's see the inductive step. So 3-cent and 5-cent stamps, limitless supply. Okay, step 1, we're going to assume P of n, that's the hypothesis. Step 2, can make n cents from 3 cents and 5 cents. So this is going to be a bit of a hand-wavy proof. But it's the idea, the intuition that's important. The mechanics are always the same, and we can formalize the mechanics. But the formal statement of making postage out of 3-cent and 5-cent stamps is really cumbersome. So let's just wave our hands for 4.5 minutes. P of n says I can make n cents from a combination of 3 cents and 5-cent stamps. Okay, we are assuming that's true. Okay. Step 3, there's 2 possibilities. Possibility 1. The solution for step 2 includes a 5-cent stamp. Possibility 2, the solution for step 2 does not include a 5-cent stamp. And one of those situations must apply, right? If we find a way to make n cents from 3s and 5s, either that solution included at least one 5-cent stamp or it didn't. Right? Those are the only possibilities. There's nothing paradoxical going on here. Okay, let's examine each of those. Case 1, the solution for n cents included a 5-cent stamp. Okay, take solution for step 2, remove a 5-cent stamp and add a 3-cent and a 3-cent stamp. And how is your postage changed if you take away a 5-cent stamp and you put on 2 3-cent stamps? Gone up by 1 cent. Since the solution here gave us n cents postage, this solution gives us n plus 1 cents postage. Okay, so total postage equals n plus 1 cents. Possibility 2, there are no 5-cent stamps. Well, if there's no 5-cent stamps, n could not have been equal to 8, because the only way we got 8 cents is a 3 and a 5. So if n is is not equal to 8, n is bigger than or equal to 9. And if it does not include a 5-cent stamp, it only includes 3-cent stamps. Now, if it's equal to 9, it's got 3 3-cent stamps. If n is bigger than 9, and it's only got 3 cents, it's got more than 3 3-cent stamps. So in case 2, the solution from step 2 includes at least 3 3-cent stamps. And so what we're going to do is remove any 3 of those 3 cents, and we're going to add 2 5 cents. If we take off 3 3-cent stamps and we add 2 5-cent stamps, how does our total postage change? Goes up by 1. We took away 9 cents, we added 10, so total postage equals n plus 1 cents. Those are the only 2 possibilities, and in either possibility we've described a way that you can make n plus 1 cents postage out of just 3s and 5s. And it's using the solution that we had for making n cents postage. So now it's turn the crank and out comes the rest of the proof. Therefore, P of n plus 1 is true, so P of n implies P of n plus 1, therefore P of n is true for all n bigger than or equal to 8 QED. Okay, so we'll start with this next time, and we'll see that there's an algorithm in here, just like with floor tiling, that actually tells us how to make n cents postage from 3-cent and 5-cent stamps. And it's an algorithm we can turn into code. All right, I will see you next time.